Yeah, in the previous post, I wrote about the LeNet architecture and also a bit of an intro of it. Today, in this video, I'll be showing you the implementation of LeNet using Pytorch. So let's just jump onto that. So as you can see, this is the architecture of LeNet. So this is primarily designed for the MNIST dataset and handwritten digit recognition tasks. So basically we have 32 by 32 images, grayscale images of that is of channel 1. So let's just first import all the required libraries. We need dot summary 2. Okay, then we create one class of LeNet. Will include the most important module class of Pytorch, which has all the methods, all the functions which we require to design or to build a neural network. Let's just write first the constructor method, and always we have to include all the functionalities of the parent class, that is the module class. So okay, now in the architecture we have three con layers in total. So let's just quickly declare that. So con 1. So it will be, yeah, it will be element dot. Okay, so channels. Okay, we'll just first declare the three con. Now, in the first one, the in channels are equal to 1 because we have grayscale images. So that's why the input channels will be 1 for the first con layer. After that, as you can see here, we are applying 6 filters. So the channel will be so output channels that we will get from first con layer would be 6. So output channels are 6, and then kernel size, as they have mentioned in the paper, it's 5, and then stride is 1, and is same, 0. Okay, for the next con layer, the input channels would be the output channels from the first layer, that is 6, and as you can see here, we are applying 16 filters, so output channels equal to 16, and kernel size is the same, 5. For the third one, yeah, we have input channels 16 and output channels 120. Kernel size 5. And also 1. Okay, these are the con layers which we'll need, and then we have 2 linear layers. So let's just layer 1, which is not linear, and it requires input channel equal to, so input channels will be 120 from the previous con layer, and output channels, as they are mentioned, it's 84. And yeah, for linear layer, we don't require kernel size and padding and right. So yeah, and for the second linear layer, we but the input channels, oh, sorry, should be input channels, not features. And output. Okay. After that, okay, so input channels would be 84, and finally the output channels 10, because as I said earlier, it was primarily designed for MNIS, so 10 for 10 digits, so we are keeping it 10. And then they also applied the subsampling, that is the average pooling. So let's just average pooling also. Kernel size is 2 and string. So we have declared all the conv linear layers and also the average pooling layer. Now we'll declare, write the forward method, and the input we can say Alex. So first start. Now we actually design our architecture. So first we'll take on one and pass our input to it. Then it will transform. Then it will go. It will require the non-linearity, that is the non-linear activation function. So as they have mentioned, they have used the 10x. So we are also going to use 10h here. We can also use, oh, we forgot to declare here. And as they have mentioned, we are using 10h, but that time the ReLU was not there. So, but obviously you can use red also. So after 10h, we apply the subsampling, that is our average pool layer. After that, the second convolutional layer. Then 10h. Average pool. Yeah, right. Okay, and after that, the third con layer. Yeah, and after third con layer, we don't require average pooling. Then input directly goes to linear layer. Dot linear. Yeah. So at this moment we get the tensor of size 120 and yeah, 120, 64 by 120, as we are going to use 64 batch size. And it's a four-dimensional tensor, 64, 121, and 1. But as we have to pass it to linear layer, we are first reshaping it. So let's just quickly reshape it. Let's print this so that we'll get to know the change in the shape of both the tensors. So maybe tensor. And after that, let's just pass it to our linear one. After that, again, we are going to apply tanh on this. And finally, the last. Yeah, I think that's pretty much of the entire architecture, and then just written in the output. Okay. Now after this, we'll just create an object of our LeNet class that we just created, and after that, we'll just create one random input for now and pass it to our LeNet class, and we'll see how we'll get the output from it. So let's just create one random tensor, and the size be 64 the batch size, and then 1 is the number of channels. So, and now save the output of our forward method into the output variable. So let's just print our model. Let's just print the summary of it. And summary function requires input shape. It needs to be passed in the input shape. So input shape is one single channel, and 32 by 32. And let's just print the output as well. Output shape. Okay, so I think that's pretty much the code we required right now. Let's just quickly run this and check our output. I'm going to run this on a separate terminal. Oh, sorry. I should call the init method. Not bad. Okay. Yeah. It should be dot summary. get the output something like this. I'll just copy it. I'll just copy paste it. So yeah. So yeah, tensor after reshaping. I mean here we get the tensor 64 4 by 120. Previously we get something like 64 121 comma 1, and then this is all the layers that we just created. Yeah, and then is the activation. This is subsampling, and here you can see the summary. When we pass the image 1 comma 32 by 32, then we get uh, 6 channels. After passing it through from the first con layer, it becomes 28 by 28 with 6 filters or 6 channels. Then after that, we get 14. That is, it becomes half after applying average pool 2D. Then yeah, you can follow along. Yes. So this much total weights or total trainable parameters we have in LeNet. And yeah, the output size finally we get is 64 by 10.